Hi, everyone. I'm Lori Cooper with the HDF group. Today, we're hosting a webinar with JP Swinski, a computer engineer at Goddard Space Flight Center. I just wanted to go over a few of the meeting mechanics. First of all, I'll be announcing a new webinar later this afternoon, so stay in touch with our forum. It's an update from Hermes, who presented earlier this month. Today, though, JP will be talking about H5Coro, the Cloud-Optimized Read-Only Library. JP tells me it's fine for you guys to interrupt during the meeting. You can ask questions if for some reason, and do that, unmute and talk. Otherwise, you can put it in the chat and I'll keep an eye on chat and I'll do the interrupting. So with that, I'll turn it over to JP.
Hey, hi, everybody. I'm just going to jump right in. So let me share my screen. Okay. Okay, can I get a thumbs up if someone can see that? Okay, excellent. Okay, so I'm going to talk about the H5Coro, the Cloud-Optimized Read-Only Library. So I have something for you guys to consider. So about a year ago, or about 6 months ago, if you had looked at the project that I'm working on, you would see that we had science product services running in AWS that were accessing H5 data in S3. We also had Python scripts written by researchers that read H5 files that were local to the computers that they were running on, desktop computers, laptops, things like that. And we had Fortran programs running on supercomputers that generated the official H5 data products for our mission. And I want you to think about this. All of those applications use the same underlying Hdf5 library. It had different languages, different hardware, different network environments, and yet all of them use the same Hdf5 library. So, first, I think that's a testament to the library that it is able to support all of those different environments. But when it comes to optimizing, the historical approach was really to tune the application use of HDF5 to get the best performance you can. So it was, how do you write the data in such a way that the chunks are lined up right, or how do you, which API calls are you going to make, things like that. But recently, and I think this is probably a shared experience for many of you, that historical approach isn't working quite so well when we move to the cloud. We're not, we've probably many of us have gone down the path of tuning our applications, and we're still not reaching the performance that we need in the cloud environments. And so, I've just listed a couple things that other efforts have done, actually, some that we've done and others that I've worked with. And I just want to say right now that what I'm going to talk about tonight, today is not to say that these other efforts are not the way to go. I think that, we should try, approaching this problem from multiple fronts.
So this is one of the bedrooms, I guess.
Okay. Oh, did someone have a question? Okay, maybe I was just unmuted. So, there are groups that have tried restructuring the H5 data inside. So you take an H5 file and you use one of the utilities that the HDF group supplies to repack the data. There's a group at Goddard that is looking at building an overlay to the data. So these DMR++ files where they index into the H5 files and allow the libraries to read those indexes and go directly into the data. And then I've talked with a good number of people that are proponents of other formats, great formats, and looking at saying, okay, well, H5 is a great archival format, but when we go for, kind of analytics in the cloud, let's transform the data into these other cloud native formats. And all of these are great approaches. But I'm going to talk about a fourth option that I'd like to add to the mix. Instead of changing the data, whether it's restructuring it, putting overlays, new format, whatever it is. Instead of changing and working with the data, change the library. So think about this. So right now, there is only a single implementation, I think in practical terms. There may have been others in the past, but in practical terms, there's only a single implementation of the HDF5 format. It's the library that we all use. And so the library actually becomes the data standard when that happens. And so the limitations of the library end up being synonymous with the limitations of the format. Lots of people have told me, well, H5 is not good in the cloud. Well, what does that mean, right? And I was one of those people 6 months ago, right? What does that mean? Well, actually, what we really mean is that the HDF5 library, as it is implemented today, is not optimized for the cloud. That's the more precise thing of way to state what we're saying. So thinking about that, I figure I'll throw all my cards on the table in the first 5 minutes and kind of give you
here. Yep. Okay.
Give you what I'd like to see happen. So if we're thinking, let's not change the data, let's change the library. What does that mean? What would be a path forward for using H5 in the cloud? The first step is, could we identify a small set of common data models that are typical for HDF5 cloud-based systems? So what I mean by this is, image data, time series data. Maybe it's just those two. Maybe it's, series data and n-dimensional data. And those are the only two data models that cover 90% of the use of HDF5 in the cloud for NASA. Or for Earth science. And then when we have that small set, could we develop and support the development of optimized implementations from scratch, right? We're developing libraries that are specifically optimized for those data models. So if you have image data in HDF5 that you want to run and use in the cloud, could you have, okay, well, we're going to have the HDF5 image data library, and it's optimized for reading image data in the cloud. Now, once you have that, you can formalize it with a standardized subset of the HDF5 specification. For instance, right, you're not going to be implementing file driver blocks. You're not going to be implementing all of the right side of the library, right? And then you still have, though, the existing HDF5 library as a catch-all utility, as a reference implementation for the specification. And I think with this in mind, there's a path forward for using HDF5 data in the cloud. And so this is my argument. I think a lot of us are faced with, well, how, all of our data is moving to cloud-based storage services. And right now, a lot of our data is H5. And so how can we use it? Are we going to be reformatting, building pipelines to transform the data into different formats? Well, this is another approach, saying, okay, well, what's the data model? Can we arrive at a few data models that capture the bulk of the data that we have? And can we build optimized libraries that specifically target that data model? And that's what we've done. And that's what I want to talk about today. So the HDF5 Cloud-Optimized Read-Only Library, H5Coro for short, is a first attempt at this new approach. And it was undertaken by ISAT2's Slide Rule project. So ISAT2 is a program out of Goddard Space Flight Center. And Slide Rule is a project under the ISAT2 program. And so what it is, H5Coro is a C++ module inside our Slide Rule servers that was written from scratch and implements a performant HDF5 reader for H5 files that are in S3. So what's our data model? Well, all our data is static. It's written once, read many, right? It was written at the time of creation, and then it never changes. We could read it today. If we go back to the same data file 3 years from now, it'll be exactly the same. Our data is time series, so we have the benefit, we know ahead of time that the data is, there's data stored sequentially in the physical memory, so we can take advantage of that. And we know that we're going to be reading it out of S3, so we have a high latency, high throughput environment. And so now, so given that data model, and I would argue that what I just described captures a large percentage of the science data that is right now being considered for S3 or is already in S3. Right? There's a couple other models, but this is, you know, a large percentage just with these 3 bullets that I've hit on. And so if we look at these, and we're not going to be clever, we're just going to say, well, if we were writing a library from scratch that had these assumptions, what would we do? How would we approach it? Well, S3 being high latency, high throughput, well, we're going to minimize the number of IO operations as best we can, right? Even if we overread some of the data, that's okay, because we're going to get killed by the number of IO operations, not the size of the IO operations. So that's our overall goal. And now how are we going to do this? Well, the data is static, so we can take advantage of caching, and not just like global caching. We can take advantage of it even locally. As we read and understand the structure of the file to get to our data, we know that structure is never going to change. So we can leverage that. And then for our data, because all of it is written at once, right? It's laid out sequentially in memory. And this, I think, is probably true for most of the H5 files. And so we can use heuristics on the range gets to S3 and be intelligent about the reads that we make. And if we have if we have data that we know is next to each other in memory, let's read it all with 1 read instead of 10 reads, things like that. So that is the super high level overview of what I'm going to talk about today. So for the rest of the talk, this is pretty much the agenda. I'm going to give a little bit of background into Slide Rule, the project that this library has come out of. I'm going to talk about the obstacles to our initial design. So about at the beginning of this year, we started our work on H5Coro, but why did we do that? Like, what were the things we were struggling with? And then the last thing, I'm going to go a little bit deeper into the H5Coro library and talk about its implementation. And again, at any point, please jump in, interrupt if you have any questions or comments. So what is Slide Rule? So Slide Rule is a server-side framework. It's in C++ and Lua. And pretty much what it does is it provides REST APIs for processing science data and returning results. So it's like an on-demand science data processing service. So if you want to take raw data and do some science processing on it, Slide Rule tries to do the heavy lifting in the cloud, gives you the higher level products that are customized for your application, and then allows you hopefully to focus on the scientists to focus on the stuff that makes them scientists, right? The actual science that they're interested in, and not the computer science of managing a cluster and all of that. The project is a collaboration between University of Washington and Goddard Space Flight Center. It is funded by the ISAT-2 program, which is an Earth science mission out of Goddard. And our initial target application is snow depth mapping and glacier research. And that's really due to the group that we're collaborating with at University of Washington. And what are our goals? These are not things that we've achieved necessarily yet, but this is what we're going for, right? It needs to be cost effective. So, near zero costs incurred when we're not in use. And this is important because you'll see how some of these goals were in jeopardy by inefficient access to the data. So yeah, we want to be able to scale up and scale down in cost. So when we're not used, almost zero, and then only pay for what we use. We want to have responsive results. We don't want to have a job-based system where someone submits a job and then walks away and then comes back and gets the result. We want to have an interactive system. It needs to have a simple API, small learning curve. We need to be able to integrate easily with other data sets, which being compatible with H5 is a huge part of. And then we need to be able to add other use cases without driving complexity. So this is what it looks like from a top-down perspective. The system is really split between the user side and the cloud side. So on the user side, right now we live in Python. So the user brings their Python script. They could be running on their desktop. They could be running in the cloud, in a different cloud, on their laptop, at work, wherever. And we provide some Python helper functions, some helper packages to interface with our system. And so then using those packages, they hit our system. Down here, you can see a slide rule. If you can see my mouse, it's just a bunch of servers running in AWS. But slide rules is also supported by some other infrastructure. We leverage the CMR system that NASA provides for indexing all of the science data products that NASA provides. And then we have some things like, service discovery and things like that are used just as a part of the infrastructure. But the heart of the system is this slide rule servers that are handle the processing requests. And then they, in turn, to get to the data, will pass that data off to HSDS, and HSDS goes and reads it out of the S3. So this was our previous architecture that we've been running with for about a year. And just for those that don't know, HSDS, I think it stands for Highly Scalable Data Service. It is the HDF cloud-based service, which we like. I mean, it's worked really well for us, despite the things I'm going to be talking about today. So this is our architecture in a nutshell. Now drilling down, because this is talk on HDF5. This is the part of our architecture specific to HDF5. So we have each server runs the slide rule application in a Docker container. Inside that application, we're linking to the HDF5 library. The HDF5 library is using the REST file connector. So the HDF5 library allows you to read H5 using different IO drivers. I think maybe a good way to think about it. So you can read to files, you can read over the network, and one of those is this REST file driver, and that is used to talk to HSDS. And so it works very well. The application has no idea that it's actually talking to HSDS. It just knows that it's talking to the HDF5 library, and the library converts all of those API function calls into whatever it needs to do to talk to HSDS. So like a read, let's say, will come through the library. The REST file will convert that to a read request to HSDS service node. The HSDS service node running in a Docker container will fan that read request out over multiple HSDS data nodes. And then those data nodes will, in parallel, look at the metadata repository, get information about the files they need to read, and then we'll go to the original files and read those files directly. And so that was our architecture for a year. So what are some of the limitations that we hit with this initial design? And some of this a year ago or 6 months ago, I talked at a HDF users group meeting and presented some of this. So if you were there, some of this you'll recognize. So there's three major limitations to this architecture. And they really hit our bottom line as far as being cost effective and responsive. So the first limitation is that all read calls into the HDF5 library are serialized. There is a global API lock. And so even if you have 10 threads running and they all make a read call in parallel, and even if those reads go to different segments of the same file or different files or whatever it is, inside the library, they're going to be serialized one after the other. The second is that HSDS issues multiple HTTP requests per H5 dataset chunk. So each dataset is divided up into individual chunks. And so if you want to read a dataset with 1,000 chunks, that's 1,000 HTTP, at least 1,000 HTTP requests that are going out to S3. And then the last is that our system required a metadata repository. So we needed to manage all of those indexes that were overlaid on top of the H5 files. We needed to create them and then pay for their storage and manage them. So let's look at each of these in a little bit more detail. So serializing. So this ended up being, this is the biggest issue. So this is the, if you just solve this, you've solved most of the problem. And it's interesting. Slide rule is capable of tremendous parallelism, and HSDS is capable of tremendous parallelism. So we have two applications that from the ground up were designed to be highly parallelized. And yet going through the Hdf5 library, all of the interactions were serialized. And so here's a trace, a logic analyzer trace of our application. And you can see this is just to prove it. I think it's important sometimes just to show that there's real numbers here. So doing one read, an H5 lib read on this thread ID, it took 21 seconds. We then issued 3 in parallel, and it's just under a factor of 3 longer. So we do gain some parallelization in the compute, but you can see the length of time for all 3 is almost 3 times greater than just one. And the reason for this is that it's all being serialized. Why does this matter? The reason this matters is that because the HDF, so you could say, I guess this is another way, well, you could say, well, why not just fork it? Like, why not just do multiple processes, right? If the Hdf5 library is not parallel, then just parallelize it at the process level or at the instance level. And I would say, okay, that's okay. Yeah, do that. I mean, applications are going to scale at the process and at the distributed level. All applications are, and that's a reasonable approach to take. But we cannot ignore the efficiency at the lower levels of parallelization. So the cost, this little diagram I have, you got asynchronous is probably the least resource intense parallelization method. Then you have threading, then you have process, then you have distributed, right? And you need all of them. And right now, the Hdf5 library is preventing the first 2. And so code constructs where I can create, 1,000 IO operations in parallel with callbacks very easily with an asynchronous method approach, right? That is not, that's very simple. Well, now I'm being forced to take those 1,000 parallel IOs and I need 1,000 Docker containers, right? Now I've got orchestration software just to manage the Docker containers because I needed to parallelize an IO read, when I could just do it simply with, some asynchronous code. Or, if you're at the 100 level, then, I can easily throw 100 threads with a couple lines of code. And it doesn't dramatically change the complexity of my software system. But as we move towards the processes and distributed parallelizations, the complexity of the software is growing much more to handle that parallelization. So that's just in a nutshell. And like I said, this is the bulk of the improvement is right here. Is can you parallelize your reads? Okay, so the second thing, I'll move a little bit quicker through this. HSDS, the architecture is per, the IO is per chunk. And so as far as the performance of a data set, the dominant factor in how quickly you can read that data set is how many chunks that data set is consistent of. So each chunk requires a TCP/IP connection, probably multiple ones, because you've got to go to the service nodes, the data nodes, and then those have to make individual requests out to S3. And so when you have H5 files with small chunks, you explode the number of TCP/IP connections that you need. It explodes. So here's a chart I showed a while ago. And I just bringing it back up for this presentation. So we took the ISAT2 data, a typical file where we're reading about 700 megabytes out of it, and we were using HSDS with the link option. And the chunks were in there when the chunks were in their original 80 kilobyte chunk size. That's this first yellow box. It took about 1,000 seconds to read. Just changing the chunk size to 50 megabytes took that number down to 60 seconds. It's a huge difference in the number of chunks. It's reading the same amount of data. The only difference is the number of chunks that compose that data. That's the only difference. And we get this, factor of 15 or something, a performance improvement. And why is that? So again, this is another chart that you guys have seen before if you attended the users group meeting. All of the performance is in these data sets that have a high number of chunks. So in the ISAT2 data, there's three groups of data sets that have 11,000 chunks each. And you can see if the seconds per byte explodes for these. So your efficiency, how long it takes to read each byte, is exploding here. And all of your time is spent in these data sets reading these chunks. And you're like, well, and just to notice, I mean, this is seconds per byte. So this is, 100 milliseconds per byte. It's tremendous. You can, it's a huge number. And why is that? Oh, so I'll jump here. It's all about the first byte latency. So if you're making small IO reads, you're dominated by your first byte latency. I measured first byte latency using CloudWatch and AWS during these tests. And CloudWatch was saying it was about 60 milliseconds. I parsed the HSDS logs. They were saying it was about 50 milliseconds. It's somewhere around there. But if you do the math, I mean, you really need to read large data sets, large blocks at a time to overcome these first byte latencies. And this is just one component, right? This is not the other TCP/IP connections that you need to make. So there's just a tremendous amount of latency per IO read. And so, well, then why not just do a better chunk size? Right? Well, that's not really going to work. It's a stopgap, but it's not an ideal solution. Like for ISAT2 data, there's really no spatial correlation, strong spatial correlation to the amount of memory in the file. So depending upon the intensity of the return, we're a point cloud. You can have lots of data points within a small spatial region or a few. And so there's no spatial correlation. You could also say, well, why not try to think, well, what's the request size going to be? Well, we're an on-demand system, so we don't know what our request size is going to be. It's user dependent. So even that. What we did do is we came up with what was called a break-even size, which is if you match the chunk size to the expected latency and throughput. So if you calculate the throughput and you multiply it by the latency, you get a certain size. If you use that, then you're mathematically guaranteed to be within no worse than a 2x performance penalty, regardless of the size of the request. And so that at least bounds the problem. But now the problem is, well, how do you know what the expected latency and throughput are in S3? I mean, we can guess them, and we did guess it, right? But there's variability even in that. That makes it not ideal. So the last obstacle is the metadata repository. So our using HSDS, we needed to create and maintain metadata indexes that HSDS used to access the data. And so, I did like a little test run just to time it. And a typical region of interest, if it's 60 granules of data for ISAT2, it took about 8 hours to load on a single instance. And so when you do the math though with that, and you think about it, the building and maintaining and running of the data pipeline needed just for the data indexes becomes an expensive proposition. So I did a back of the envelope, and for ISAT2, for our mission, it produces about 150 terabytes of data each year. And so if we were loading and maintaining, loading, rechunking, building the indexes, and maintaining our own data sets, we would need to run 4 EC2 instances, 365 days a year, 24 hours a day, all the time, just to keep up with the new ISAT data that is being produced. That means that same 4 EC2 pipeline, if to go back a year, would take a year to load that. So if we wanted to get 2019 into our system, we'd have to, and we started today with 4 EC2 instances. Well, a year from today, we'd have 2019 loaded and ready to go. And so this becomes its own project. It really, even though it's technically simple, logistically, it's a problem. Okay, so with that in mind, pivoting now to H5Coro. So this is what we tried to overcome in this H5Coro design. So where this fits in is, instead of having the HSDS services running in Docker, we pull that in, all that functionality becomes just a small library that we link into the slide rule application. So now our system looks like that. And drilling down again, so this diagram that we showed before up at the top is the previous architecture. We have the Hdf5 library, talking to REST val, talking to the service nodes, fanning out to the data nodes, going to the metadata repository and the local files. That's now been replaced by a small, very specific implementation, targeted implementation of the H5 spec called H5Coro, and that directly goes to the H5 files. It doesn't need anything else. So what the key features of the library that make a difference for us? So the first is that all of the reads are concurrent. So if you have multiple threads and you're doing IO reads in parallel, those reads are executing in parallel. And if you've got multi-cores, they're actually happening at the exact same time. But even without that, because most of your time is spent waiting for IO, it's tremendously efficient. The second thing is that we use intelligent range gets to read as much data as we can with each IO. So if you have a data set that has 20 chunks and you're subsetting that data set and you need to read 15 of the chunks, it will do the best it can to read those 15 chunks with one IO read. It'll not split them up into 15 reads. It'll say, oh, it looks like these 15 chunks are next to each other. I bet you we can get that with one read. And it estimates the start of the location of memory, and it estimates the end of the location of memory, and it does one read. And if it misses a little bit, it then goes and corrects. But even if it has to do 1 or 2 corrections, follow-up reads, it's still much better than doing 15 reads. The third thing is that the system is serverless. This just makes it easier to scale and manage. So we just link it in. It just links into our C code. And then the last is that we don't have a metadata repository. So I'll talk about this a little bit later, but we made a decision, instead of caching the data that we're reading, it doesn't ever cache the data. It caches the metadata. So it turns out when you're reading, for us at least, we read multiple data sets from each file. And all of the internal H5 structure is usually located near each other. For the ISAT2 data, it's in the beginning of the file. Actually, I was working with someone recently with seismic data, and they sent me some files, and their metadata was at the end of the file, which was a little weird, but it was still all near each other. And so by caching the metadata, one, it's smaller, so I get a lot more bang for my buck as far as the cache. But two, I know I'm going to have to reread that metadata as I read other data sets. And so it gets a high hit level. So by caching that, we actually didn't need to build external indexes. The raw read starting with a file from scratch was fast enough that we don't need any metadata repository. So it's, where does the rubber meet the road with actual performance numbers? So we did a test. I constructed tried to construct a typical scenario for our use case. This test read the data in multiple ways. It was about 66 granules. Each of the granules are about 2 gigabytes in size. Everything was running in AWS US West 2. And it was run, I was hitting it with a Python script from my home computer. So I did some test runs just to see what the performance was. And so we had H5Coro running in slide rule on an EC2, and we had HSDS running on a different EC2 with slide rule.
Hey, JP, I wanted to interrupt real quick. We have a
Yes.
question in chat. Is the metadata caching something that happens in H5Coro or slide rule?
It happens in H5Coro. Yeah. So it's a part of the library. Yeah, that's a good question.
He says, awesome, thanks. Feel free to unmute yourselves if you guys want to ask, but I'm happy to grab things out of the chat too. Thanks.
So, and I'll just caveat, testing is hard. Like getting real performance numbers is really hard. There's a tremendous number of variables. So please just take this as like a sampling. I'm giving you numbers with like multiple significant digits, but it's really just a sample of the performance. So the table here is ordered by the duration. So the things that took the setups that took the longest are at the top, and the setups that took the shortest amount of time are at the bottom. So and we're looking for low numbers, right? So we want to run this test, and we want to be able to process the data and read the data as quickly as possible. So the smaller the number, the better. The shorter amount of time it takes, the better. So the longest run was the HDF5 with the rest file, reading in S3 with the original ISAT2 data. So in our test of 66 granules, processing 66 granules, it took about 9,500 seconds, or just over 2.5 hours, to read that data out of S3 and process it. Our next jump down is when we use the pipeline and we repackage that data. So we change the chunk size from 80 kilobytes to 50 megabytes. And that took it down to 3,000 seconds, about a factor of 3. And now the reason why you see not as much of an improvement as you did in the other charts is because this is subsetted data. And so now actually the large chunk size penalizes you a little bit, because you are getting inefficiencies at the edges of your subsetted region. But it's still a huge improvement. I mean, a factor of 3 is significant. Then our next jump down is using the H5Coro library. We get on the repacked data, we get a factor of 10 improvement. On top of that, just using H5Coro. So you can see, even with the large chunk size, H5Coro is a significant improvement over the HDF5 REST file approach. But now, because H5Coro has a heuristic for intelligent range gets, we can now go back to the original data sets. So we don't have to have a pipeline, and we actually have a better performance because we're not overreading at the edges. And so now, using H5Coro reading from S3 with the original files, this line in yellow here, our target, it's reading that data set in just under 2 minutes. So we have the same data set, the same processing, and using the Hdf5 library, reading that data set and processing it took just over 2.5 hours. Now the same processing, the only change we made was we replaced the Hdf5 library with H5Coro, and really the only difference there is it's a targeted implementation for the S3 environment, and we get 2.5 hours down to 2 minutes. So, depending, you can always look at these in different ways. If you look at the original data sets when no caching is used, H5Coro is a factor of, when you add it all up, it's 77 times faster in our testing than Hdf5 library. Now, when you factor in caching for both, caching on the HSDS side and caching on H5Coro, then it goes up to about 132x performance increase. And just to put that in practical terms, in our system today, our system in January was taking about an hour and a half for typical processing regions, not test cases, but the normal use cases that we were hitting it with. And now those cases are being handled in 25 seconds. So we really have gone from a batch job approach to now it's getting much closer to real-time response, where someone types it in and then waits at the keyboard for the answer. And certainly we could scale that up and get even better performance there. So what does this all look like? I apologize for those that are not C programmers. I think for those that are, it demystifies what's happening just by seeing the API. So there's pretty much just one API right now in H5Coro, and that's reading. And so here's the read call. So you make a call, you give it a URL, which is like S3, my bucket, my folder, my file, right? So now that's the path to the file in S3 that you want to read. Then you give the full path to the dataset name, / my dataset. You give it the value type that you want returned. So if you want it to be returned as integers or floats, you tell it that. Typically though, the way we use it is we say dynamic, which means it just reads it in the native format that it is stored in the file, and then it tells you what that format is, and then you're responsible for casting the data return to the format that you needed it, and that's much more efficient. You tell it if you have multi-dimensional data sets, you tell it which column you want in the start and the stop rows. If you have more than 2 dimensions, it collapses all the dimensions above that together in the data set that it returns. There's a context that you pass in. This is used so that if you're reading multiple data sets from a single file, it'll hold all the cache information about that file together. And then this is what's returned. It's just a structure of the data that you've read, along with any of the metadata like the size and the type. So that's it. I mean, that's in a nutshell, that's what it does. It's just reading data sets. And then there's yes.
Okay, so the chat is blowing up with questions, and
Yeah.
also I think our dog is making a crazy noise. Hopefully you can't hang on. Oh, it's not a dog, it's a toddler. Sorry. Hang on, Cooper. So there's someone says, interesting use case, very relevant. What's the code maturity and licensing model? And is it in the public domain? And how could collaboration opportunities be explored?
Okay, yeah, so here, let me get this back up. Yeah, so good question. So the code is open sourced under the BSD 3 clause license by University of Washington. So we have the University of Washington has a GitHub repository that they've open sourced this code under, and it's open source under BSD 3. It is, so the code was is about 2 months old at this point, 2 to 3 months old. It's being used every day for us, but it is far from mature. And so it's now we have switched for slide rule. Slide rule has been in existence for just over a year, and we just transitioned to this library about a month ago in our our production system. So we're comfortable enough that it's fine for the ISAT2 data. We've done enough testing to convince ourselves that it's fine for the ISAT2 data. but it is not, it's not like, yeah, like if you were gonna throw it data it's never seen before, I guarantee you we'll find something. And so our hope is to continue to support and grow and mature this. And I fully welcome anybody that thinks that they're, we could benefit each other by working on this together. That would be awesome. But it's, we're hoping that we'll go towards a more mature, complete solution.
JP, any links you wanted me to share with the community, you can email those and I'll include those with the recording and the slides. So
Okay, yeah.
More questions. My coworker, John Mainzer, do you have performance data for read-only S3 VFD with or without page allocation, page buffer?
With or without page allocation or page buffering? Are you talking about going to the local file system?
No, the read-only S3 VFD is supposed to talk to S3 directly. If you used paged allocation and page buffering, you ought to be able to bring in the metadata in a fairly small number of reads. For the raw data, unfortunately, right now it would still be serialized, but I was wondering if you'd investigated that at all.
I am not clear on what you're asking, and maybe we can take it offline.
No
Yeah.
problem.
It is. I've seen for the ISAT2 data, it takes about 5 reads to get all of the metadata in for a file.
Mm-hmm.
Those are range gets, HTTP range get requests to S3.
Mm-hmm.
The cache line size I've set is, I think, 1 meg, and so I could increase that, but then there's some tweaking there because then you overread, and so that's where it is right now. H5Coro does go to does work with local files just because I needed to, and in local files, the performance is just dominated by the OS buffering of the file. So the files, pulling the file into memory by the OS is like twice.
We should chat offline.
Yeah, so and feel free, anyone, to post questions like on the webinar announcement or just ask in our forum, hopefully, or we'll you can find contact information for JP, but we're happy to facilitate communication as much as we can too for the community. Okay, yeah, we have several more questions. So Robert Casey says, terrific presentation. With H5Coro, do you contend that it is more efficient to maintain byte offset information for data within the H5 file versus maintaining this offset information in a central database?
Yeah, good question. So, so all the byte offset information, H5Coro does maintain a global dataset cache inside itself. So each instance will remember the data sets that it's read. And the reason it does that is it's not relied on for the performance. So the numbers that I'm quoting you don't use this. But I added it because it's almost for free. I mean, so you only need a couple, like 100 some bytes to store all the meta information you need for a data set. And so I can store like 100,000 data sets in local caches and then rotate them out based on their usage pretty easily. So I do that. You would definitely improve if you had a metadata repository. You would improve performance. You could get all the metadata for a data set with 1 read every time, and I'm doing it on average in 5 reads. So you will definitely improve performance. The question is the logistical cost of maintaining the metadata repository sufficiently low that it merits it? And that's probably you're probably going to get different answers for different people. We're a low budget, and so cost is a big deal for us. Now, like if NASA is deploying, like with their Cumulus program, I think they are going to supply indexes, and I think that's awesome. they have the resources to build those indexes and maintain those indexes, and we'll all benefit from it. And when those indexes go live, like, we'll use them. But we wanted this library to work for everyone. And so we, from the beginning, said we need to get this performant without going to a metadata repository. And so for us, we're now bottlenecking on other things. So what was the tall pole, which was access to H5, is no longer our performance bottleneck. So I'm not even working performance improvements to this right now for us, because it would give us almost nothing, because there's other parts of our system that we need to optimize now. Is that what you answer?
Yeah, that was a great answer. Thank you.
Oh, okay.
Okay, here's another question. You might have said this earlier. Is there a Python binding for H5Coro lib? Could there be a native Python version of H5Coro that would maintain the efficiency?
Yeah, that's a good question too. So, okay, so slide rule, you can compile H5. So we provide Python bindings. So if you're comfortable building slide rule as a shared object from C, you clone the repo, set up your CMake, and you build it. You can build it as a static library or as a shared object. We provide Python bindings where you can then import that slide rule Python bindings right into your Python application and use H5Coro from a Python program natively. But for those that are familiar with Python and packaging, that is kind of a complicated method, because that means every architecture, if you're on Ubuntu 16, Ubuntu 20, Ubuntu 18, whatever, you're gonna have to build your own. If you're on CentOS, if you're on Debian, whatever it is, you're gonna be building your own. If you're on Mac, you're gonna be building your own. You're responsible for building it. Now, if you're comfortable building, shared objects from C repositories, we have the Python bindings, and I use them, and they're tested. I looked at, doing like a many Linux build to try to support, like a pip install. It's not trivial. Specifically right now, the dependencies to the AWS SDK are not trivial. And so that development environment is a little bit complex. I'm looking, actually, one of the things I want to do is try to remove the dependencies to the AWS SDK, and that would greatly simplify this entire effort. But until then, I think the best way to go would be, if someone was interested in having a native Python library like this, is the H5Coro took me about 6 weeks to develop, and I had never looked at the spec before. And so I imagine someone familiar with HDF5 that's kind of lived in this world at this level before, and as a comfortable Python programmer, it's not months to develop it. It's probably weeks to develop it.
I
So
believe
that would be my recommendation, is to do a pure Python implementation.
I believe my question is next, and it just so happens you gave me a fantastic lead in there. I program in the ZAR and Fspec in Python primarily. Quick comment on your packaging thing, you might want to check out CondaForge for doing the packaging for Python bindings. But it just so happens that I've approached this same problem from a slightly different angle in a small project called Fspec Reference Maker, which I can link, which basically provides like a virtual file system view into an HDF, one or more HDF5 files, which you can then read with the ZAR library. And that means that you A, cache the metadata, as you're saying, and you B, get concurrent reads on the chunks. So you get much of the performance gains that you're talking about here. In the current implementation, we do store those metadata as files, as indexes effectively, and we don't do the intelligent range merges that you do, which obviously is a big part of what you've done here. I think there's definitely it would be interesting to see to what extent those two things can be merged together. What I find is interesting about the project that I've done is that it's not just HDF. You can use this for different types of files that embed basically C buffers at some level. They're all C buffers, right? So TIFF file, other things work with this concept, but it will never be as well tuned and as performant as something that you make where you really understand the underlying data structure as you do.
Oh, that's interesting.
Should I put a link?
Yeah, that would be great. I'd love to look at what you're doing. Yeah.
So I'll provide the link to the repo that does the joining up of things, if you like, that does the indexing.
Yeah,
Yeah,
that'd be great.
yeah, the chat's been pretty busy, so I'll post the file of the chat on the forum too, so you guys can look over it. With just a few
I
minutes.
should have mentioned on that, sorry, that if you're doing this process with Fspec Reference Maker, you don't actually need the Hdf5 library to read the data set anymore, which is weird and interesting. Sorry, that's it from me.
Okay. Yeah, no, that sounds really exciting. I'd love to look at it.
So I think I'll just grab like one more question here. So yeah, Jim asked, are there any limitations you found, file size limit versus a large number of files?
No, that's a good question. So I go through, actually, for those, I'm just going to skip through. I do talk about which parts of the spec are supported and all that, but the limitation is inside H5Coro. The biggest thing is just that it's parallel. That's like the biggest bang for the buck. After that, it's the intelligent range gets. Now, to do the intelligent range gets, what you're doing is there's a heuristic in the library that tries to predict the start and the stop of sequential memory and combine the reads. For time series data, that's not that hard. For two-dimensional data, for image data, depending on the way you're slicing it and depending on the way that the data is stored, it becomes a little bit more of a difficult problem. I would argue that this approach still works, that you still could develop heuristics that minimize the IO reads an order of magnitude and see some of the same performance benefits. So I would not say that the limitations are necessarily on the size of the file, though I'm sure maybe at the extremely small files, at some point you're just kind of bumping up against what S3 is meant to be. And if at some point you're no longer should be going to S3, you should be going to a database if you're trying to read like small little objects. But other than that, I wouldn't say the limitations are there. I think the limitations and what's going to take work is knowing the different types of data and trying to come up with some generic heuristics that work with most of them. And so we've done an easy case with time series data. I think there's a path for 2D data, but it's not like a out of the box what H5Coro would be great for. It'll work, but it would not be as performant as if you targeted it for that data model.
Okay, I think with that, we're going to wrap up. So I will post the chat transcript and send that to JP. Feel free to continue the conversation on our forum.hdfgroup.org. JP, thank you so much for your time in giving this presentation today. We really appreciate it. I will try to get the recording up early next week. It will be on YouTube. I'll post it on the forum and the chat transcript as well, and JP's slides and any links he wants to send me. So thank you, everyone. Bye-bye. Have a good weekend.
Okay, thank you.